Okay, welcome back. This is video 2 of the Investigation 9.2b Iodometric Titration of vitamin C. Alright, in this video I'm going to take you through the process once and we're going to check our values so you can then refresh and then try it on your own. Okay, so our goal for this is, if you click right here, it says our goal is to perform a titration experiment to determine the concentration of ascorbic acid in 1 medium peach 10 milliliters of solution. All right, so we can check this. We're going to click on Wikipedia here, and this will take you to the vitamin C page on Wikipedia. And if you scroll down into the contents, go to sources. It says a cherry or a peach has 7 milligrams per 100 gram peach. Okay, so our solution, our 10 mils of solution, is equivalent to 100 grams of peach, so we should be around about 7 milligrams when all is said and done. Okay, so one more time, let's just take a look through here. So we have all of our solutions, and we also have a bunch of glassware to use. The ones that are important for us today are the Erlenmeyer flasks. Okay, for our sample, we will need a volumetric flask to mix up our stock solution of potassium iodate, and we will need a burette, which is found under Other, okay, a 50 ml burette. The tools you have available are a Bunsen burner and a scale. You're not going to need them today. Okay, so let's take care of our stock solution. So let's take care and look at these reactions again. Move myself out of the way here. Okay, so these are the two reactions. So just to refresh, we are reacting potassium iodate with potassium iodide to form iodine. Okay, this happens in an excess of acid. We're using HCl. All right, we have an excess of Ki. All right, so the only thing that matters for us is KiO3. We're going to measure this really precisely because these are in excess. They're not going to affect our results. We're using this KiO3. 1 mole of KiO3 produces 3 moles of iodine. Those 3 moles of iodine go on to react with the ascorbic acid in a 1-to-1 ratio. Okay? These react and they produce some products. All right, but what's important for this titration is that as soon as this acid is gone, we have excess iodine remaining. This iodine will react with starch to form the starch-iodine complex, which has a dark, dark blue-black color. Okay, so there's our reaction. So what we have to do is we're going to calculate the amount of, or the concentration of potassium iodate stock solution we're going to make. All right, we're going to make 250 mils of this. All right, and I'm going to use that value they had up here to kind of calculate a roundabout number. I know that the stock solution they give me for ascorbic acid has 0.01136 molar. Okay, so that is 0.1136 moles per cubic decimeter. And this gives us 10 milligrams of ascorbic acid in each 5 mils. So it's roughly 3 times more concentrated than our sample will be. All right, so but it's a good starting place for us to calculate our solution of KiO3 very precisely. Okay, so I'm going to start with that solution right here, 0.01136 moles of C6H8O6, that's our ascorbic acid, in 1 cubic decimeter. All right, our sample is going to have 10 milliliters, so 0.01000 cubic decimeters. Okay, and we'll type it in the calculator here, 0.01136 times 0.01000 says that we have 1.140. It rounded it off for me. Well, that's not cool. We need to go more precise than that. So 1.136 times 10 to the negative 4 moles of C6H8O6 in this solution here. 10 mils of this solution has 1.136 times 10 to the negative 4 moles of ascorbic acid. Okay, concentration times volume equals moles. All right, so I want to find how many moles of potassium iodate I need to carry out this reaction. Okay, so I'm going to use some mole ratios here. 1 mole of ascorbic acid reacts with 1 mole of iodine. So I can find out how many moles of iodine I'm going to need. One mole of iodine, 1 mole C6H8O6. Okay. And then 3 moles of iodine react from, or form from, 1 mole of potassium iodate. Okay, so 1 mole KiO3 over 3 moles of our iodine. Okay, so we see that 1 mole of our ascorbic acid reacts with, or 3 moles of our ascorbic acid react with 1 mole of our potassium iodate, according to this. Okay, so we do that math, and let's see if the calculator wants to mess with me again. 1.136 times, I'll do that here, times 10 to the negative 4 times nothing divided by 3. Yep, and it rounded it again on me, so I'm going to give you the true value here, 3.7867. I'm carrying extra sig figs so I don't introduce any error, times 10 to the negative 5 moles of KiO3. You guys can't see that because it's off the side of the page. I'm going to switch calculators. So that one is bugging me. This one's a little harder to see, is why I wasn't using it. Okay, so this 3.7867 times 10 to the negative 5 moles. All right, I want to use about 10 mils, I think, in this titration. All right, I'm just picking that value so that it's less than 50. That's what the burette holds. All right, that means I would be able to do several titrations without refilling the burette. So 10 mils is a good value here. I want to have this many moles of KiO3 in 10 mils, so I can calculate the concentration using that, because moles divided by volume is concentration. So 3.7867 times 10 to the negative 5 moles divided by 0.010000, sorry, too many zeros, just 3 zeros. Okay, so 3.7867 times 10 to the negative 5 divided by 0.01 should give me 0.0037867. Okay, so that's 3.7867 times 10 to the negative 3 moles per cubic decimeter KiO3. All right, so that's exactly how much. That's a really finicky number. It would be hard to get that mass, probably. So I'm going to make this a little easier by just estimating this. Okay, we're going to say we want 4.0 times 10 to the negative 3 moles per cubic decimeter KiO3 solution. All right, so now I'm using solid to make this and some distilled water, so I'm going to use the concentration times volume solution to find moles, and then multiply by molar mass to find the mass of KiO3 we're going to use. Okay, so moles KiO3, concentration is going to be 4.000 times 10 to the negative 3 moles per cubic decimeter. And I'm going to make 250 mils of solution, so 0.2500 cubic decimeters. All right, and no, you can't see that, so 0.001 moles. And that does have 4 sig figs, so 1000 moles potassium iodate. Okay, and in the lab it tells me that the molar mass of potassium iodate is 214.001. So we're going to use that value, multiply moles times molar mass. To find the mass we need, and that is going to be, so we're going to take that number times 214.001. We need 0.2140 grams of potassium iodate to make our stock solution. All right, so now we're going to go back to the lab space. I'm going to get rid of my face here so you can see the whole thing. That got rid of me. I'll put myself way up here. Okay, so we're back at our lab space. I'm going to get a volumetric flask because we mix solutions in volumetric flasks. All right, so I'm going to grab a 250 ml volumetric flask. I'm going to rename this by right-clicking on it and clicking Rename. This is going to be our 0.004000 molar KIO3. Okay, so right now it's empty, so we have nothing over here in our information tab. So if I click back on the stock room, I can go to Solutions, and I want my potassium iodate solid. All I need to do is click on it and it appears. So to get this one into this one, I click on it and drag it over until I see the plus sign. When I let go, now I'm in pouring mode. We're just going to use the precise, and I'm going to type in the amount that I want, 0.2140 grams. And I'm going to click pour. It says 0.21 grams transferred. Okay, so that's as precise as it's going to get for us. We have to assume that's precise enough. So I can click back on this KIO3 and I can remove it by right-clicking on it and selecting remove. So now my volumetric flask has 0.214000 grams of KIO3 in it. And notice it has a volume here. That small amount of potassium iodate is taking up some space. So I can't just pour 250 mils of water in here to make my solution. Okay? So I have to be careful. I don't want to fill over this line. I can grab the distilled water from the stockroom and I drag it over until I see the plus sign. Alright, now we're in pour mode. So there's my line. I don't want to go above that. Alright, it says there's 0.05 milliliters already in the flask, and this is a 250 ml flask, so I'm going to pour 249. Okay, so now we're pretty close. We're at 249.05. So it's tempting just to type in another number and hit pour, but that will screw you over because this doesn't erase. Okay, you need to delete that, and then we're going to add 0.95 milliliters. That ought to take this bottom of this meniscus right to the line for a perfect pour. There we go. Okay, we have exactly 250.00 milliliters or cubic centimeters in our volumetric flask. All right, excellent. We can get rid of this giant carboy of water by right-clicking and removing. So good, we have our stock solution. Excellent. Next task is to make our sample. So glassware again, Erlenmeyer. We're going to use a 250 ml Erlenmeyer flask. Again, I'm going to rename this by right-clicking on it, renaming it sample. Always label your glassware so you know what's in it. Okay, so here's our sample flask. Go back to the stock room, and in the solutions now, we want, and we can always check back up here, we want 10 milliliters of the peach solution, 5 milliliters of KI, 4 milliliters of HCl, and 3 milliliters of starch. Okay, and all of this goes in our sample flask. We need our sample. We need our potassium iodide to form the iodine. That's our reactant. We need HCl. We need acidic conditions for this. That provides the acid. And we need the starch. That's our indicator to tell us the reaction is over. Okay, so I have all 4 of these solutions here. And just like before, we're going to drag it over till we see the plus, and we're going to pour. So I want 10 milliliters of the peach solution. I'm going to go 5 sig figs on that just to be safe. Probably don't need it. Okay, it's 10 milliliters transferred. Good. Potassium iodide, we needed 5 milliliters. And that wasn't as important, so 5. And good. Acid, 4 milliliters. 4, pour, all set. Starch, 3 milliliters. 3, pour, all set. Okay, so now when I click on the sample, my information tab here tells me it's sample. I have 22 milliliters total in my flask, and it's listing out the concentration in molarity, that's moles per cubic decimeter, of every species in that flask other than water. Okay, so we have acid, we have 0.363 molar acid. We do have some hydroxide, but it's very, very, very not concentrated, so it's probably not going to affect anything. 10 to the negative 14 here. We do have our peach and our ascorbic acid. It doesn't give us concentrations on those because that's what we're calculating. We have potassium and iodide and chloride ions from the potassium iodide and the hydrochloric acid. Those are their concentrations. And then we have a very little amount of starch. And then it gives us pH at the very bottom. Okay, so that's all the information on our flask. All right, the last thing to do is to titrate. So we're going to go back to the stockroom. We're going to go to glassware again, go to Other, grab a burette. This is a 50 ml burette. Just remove my sample out of the way there. We're going to take our stock solution here, our 0.004 molar potassium iodate, and we're going to fill this burette. So I'm going to enter, it's a 50 ml burette, so I'm going to pour 50 mils in it. Oh, and it only goes to 2. Okay, remember burettes count up, so we want this to go to 0. Those extra 2 milliliters we're missing here probably went to fill the bottom. All right, it's not going to affect our calculation. All we need is a start and end, but we like to start at 0. So I'm going to delete my 50 and add 2 more in. It does tell me there's 50 poured. It has exactly 50 mils in it. We're going to pour it in there. Okay, now we're exactly at 0. So that's our starting point. 0 milliliters is our starting point. Now we're ready to titrate. Okay, so I'm going to take my sample and put it to the side, grab the burette and drag it on. Okay, so go slow here. If you go past, you will have to start over, and I mean over from the beginning. Okay, there is no going back. So go slow. All right, I'm going to start with 0.5 milliliters per pour. Okay, and I'm going to pour this a few times. I know about how much this is going to take, so I'm going to do this a little bit faster, but you want to be careful. Okay, so when I hit and poured that half a mil in there, I went from 0 to 0.5. All right, notice our values over here have changed. Okay, we have iodate, iodine, we have our starch iodine complex. They're all about 0. They're very, very low concentrations because they're being used up at the moment. Okay, or they just haven't formed yet. All right, but these values will go down and these ones will eventually come up. So let's keep pouring. There's 1 mil total, 1.5 total, 2 mils, 2.5. I'm getting a little nervous. I'm going to slow this down to 0.1. All right, this isn't like a real titration where you'll get some indication that you're close. This just kind of happens all at once. Okay, so go slow. 0.1 milliliters. So there's 2.7, 2.8, 2.9, 3. Okay, remember we calculated that the stock solution, which was roughly 3 times as concentrated, would take us 10 mils. So this ought to take right around 3.3 mils. So I'm going to go even slower here. We're at 3. I'm going to go to 0.05. Okay, so I'm watching closely. I'm watching these values here, and I'm watching the color of my sample. 4, there's 3.1, 3.15. All right, so it took 3.15 milliliters of our potassium iodate to turn the sample this dark blue, black, purple color. Okay, 3.15. So I'm going to write that down. I'm writing on my pad of paper here. We started at 0, we ended at 3.150. So we have 3.150 cubic centimeters used. Okay? I'm going to keep titrating just a little bit just to make sure that it doesn't change anymore. And nope, it's not changing anymore. We can see the concentrations going up over here. Okay, so there's our data. We used 10 mils of the peach solution, and we used 3.150 cubic centimeters of 0.004000 moles per cubic decimeter potassium iodate. So let's calculate. Back to my pad of paper here. We use 3.150 cubic centimeters of potassium iodate. So let's figure out how many moles of this we used, and then we can use these mole ratios to calculate how much or how many moles of ascorbic acid there was. Once we know that, it's a hop, skip, and a jump to mass, and then to milligrams. Okay, so 3.150 cubic centimeters. So the moles of KiO3 used equals concentration times volume. So our volume was 0.003150 cubic decimeters, and this is 4.000 times 10 to the negative 3 moles per cubic decimeter. Okay, my handy dandy calculator, which you can't see. I'm going to put it here. I'll type it in and you can see it. There we go. 0.0031 times 4.000 times 10 to the negative 3, and it tells me 1.260 times 10 to the negative 5. That is moles of KiO3. Okay, and then 1 mole of potassium iodate gives us 3 moles of iodide, and then 1 mole of iodine, and then 1 mole of iodine gives us 1 mole of potassium or ascorbic acid. So 1 mole of potassium iodate gives us 3 moles of ascorbic acid. And there we are. 3.780 times 10 to the negative 5 moles ascorbic acid. Okay, so the last part here is to find the mass. How many milligrams of ascorbic acid were there in this sample? So that's how many moles there were. We need milligrams. And if I can go up any further. There we go. 3.780 times 10 to the negative 5 moles ascorbic acid times its molar mass. The molar mass of ascorbic acid is down here. The molar mass for ascorbic acid, 176.124. Okay, so this gives me grams. I want milligrams. So if you need to look it up, that's fine. I had to earlier. 10 to the 3 milligrams, so 1,000 milligrams in 1 gram. Okay, so a little hard for you to see. There we go. 3.780 times 10 to the negative 5 times 176.124 times 1,000. We have 6.6574 rounded to 4 sig figs, 6.657 milligrams of ascorbic acid in this sample. Alright, and that's near 7, so that's pretty good, that's hopeful. Let's see what the simulation says. I'm going to type this in here, 6.657. Okay, 4 sig figs. And we'll check this. There we go. All done. Alright, success, well done, you did a good job, and it tells you what the actual value is down here. So medium peach contains about 6.6. This one contains 6.627. We got 6.657. That is really good. We're within, I don't know, 100th of a milligram. So it's really precise. Okay? Excellent. Once you have this, you will write it up, show your work, okay, and give us this screenshot of this success screen, right, and that will call it done. I will type up the directions for how to turn this in and what you actually need to do. I'll put them on Classroom. May the force be with you. Good luck.